Um, on your homework, some of you, you hit that, please, thank you. On your homework, some of you are not giving me the 4 things I expect in such a problem that I would take off for, not on the homework, but on a test or a homework quiz. So, I expect these 4 things. P series. It doesn't go without saying. P equal 2/3, which is less than or equal to 1, and therefore diverges. I require those 4 things. Identify as a p-series. Give what the p-value is. Give the test comparison that tells you what's happening, and then answer the question divergent. You must give me those 4 things. Get in the habit, practice it, please. Some of you are practicing bad habits. This one, how did you approach the next one? First thing you should always check is, do the terms, the divergence term, do the terms go to 0? Does it even have a chance? This, definitely not. The terms go to infinity. You're adding infinitely many, infinitely large terms. That's not happening. Okay? So divergence. Divergence term. What was your approach here? Integral test. When you do an integral test, I believe Elizabeth asked about this, but you should be using x's, not n's. Also, to a, this is fairly arbitrary. I typically just use this value, and that's fine, but it doesn't even really matter because it's all about the infiniteness, not about the finiteness. So, to what it converges, let's go here. If this were 2 or 3, then we would get a different numerical answer if it converged. Do you agree? Yeah. But the question isn't, what does it converge to? I don't care. It just, does it converge or not? So it wouldn't matter if this is true. It doesn't matter. Okay? Next, I have talked a wee bit about if this integral is complicated or requires some advanced integration technique, then I recommend you do the antiderivative in an indefinite integral off to the side, rather than use something here, which would require you to change that and that. All right. So if you get a complicated integral, if you can do this mentally, fine. I'm fine with that. But if you need to use sub this, then I would suggest you do it off to the side and get something like natural log of the absolute value u. If you get the natural log of the natural log of x, I guess that one's just x, not absolute value, then that's my antiderivative. So that looks something like the limit as a goes to infinity of the natural log of the natural log of x from 2 to a. Also, some of you are taking a little liberties on combining steps. You do not anti-differentiate and evaluate in the same step. That's a no-no. Okay, you don't do that. I will count off on the test. They will count off in the AP test. You need to show the antiderivative, then show evaluation in separate steps, please. And natural log of a minus natural log of 2. And so, what does it go to? Infinity. Am I done? No. Am I done? No. Hey, you just proved that the integral diverges. That wasn't the question. The question is, does the series diverge? So your conclusion is a sentence. The series diverges because the integral diverges. It is not say diverge and circle it. It's give a conclusion. Okay? And the last one, I suppose you could do an integral test for that. It integrates pretty nice, but I was hoping you would do direct comparison. Did you?
Yeah. I have a question about just like what work to show. Can you plug in like a into and the at the same time? Like, could I just go straight to natural log of infinity minus natural log of 2?
I don't see one.
Okay.
Direct comparison steps. I'm going to go that way. If you did the integral test, that's fine, but I'm going to do the direct comparison test. What did you compare it to, if you did? 1 over n, okay, which obviously you want to compare it to something you know the convergence or divergence of. We all know that diverges. In this case, we have to hope it's the half of the cases that work and is conclusive. N minus 1 is less than n, would you agree? Therefore, 1 over n minus 1 is greater than 1 over n, would you agree? And the sum of lots of those terms must be greater than the sum of lots of those terms. I think you'll agree. Now we know this to be infinite, and our series is greater. So we can. Does that prove divergence? It does. Okay. The series 1 over n minus 1, or just the series, whatever you want, diverges because what?
Because it's greater than.
It's greater than the other one. 1 over n, which diverges. Why do you say that? Armand. All right. Are you with me? Are those going okay? Cool. Here's the plan. I know it feels like, ooh, only front page and notes. This will take no time whatsoever. But quite the opposite, quite frankly. We'll get to maybe the front side. Maybe. As the bell rings, we'll get through it. And we will most definitely not get to questions on the front sheet, so that'll be pushed up tomorrow. This is going to take a while. It takes some serious thought, so I hope you ate your Wheaties, all right? Okay, first thing before I even start is I've got to communicate to you the importance of speaking up. These are hard. They are a disaster for the first few weeks, and there are numerous approaches to these problems. It is crucial that if you did it a different way, you say so. Because first of all, somebody else might say, oh, that way makes way more sense than Rick's way. And it's important that you say this, that's valid too. Okay, so you've got to speak up for yourself. There's some really cool, creative, problem-solving opportunities here to be had. Right? First thing, I didn't like this, so let's call this 2, please. Would you change R1 to 2? I'm going to put the big idea here. I meant to put a big old formula box here, but I forgot. Let me go there. This is going to be the area between two curves. Now, I don't know where I'm going to put this. I'm going to do it over here. Okay, imagine if I had a limaçon and a circle, and I wanted the area inside the limaçon, outside the circle. Okay. Now remember that these aren't rectangles; they're sectors. The whole idea on the formula is based on either sectors or triangles, depending on how you look at it. But when I draw area under the curve rectangle, I think, okay, what do the rectangles look like? But when I do polar area, I say, what do the sectors look like?
Oh, no.
That's old. What are you talking about? Oh, no. That's how it's always been. Hang on a second for your own. No, it's not time yet. Okay? So this region would surely be the region all the way out. Take away the region in, yeah? This region, take away this region, leaves the outer region. So what do you reckon the approach is going to be? If I call this R1 and this R2, then how would you find the region all the way out? 1/2 all the way out to R1 squared d theta, yeah? And we're going to subtract the region R2 squared d theta. Now because they share a half and they'll have the same bounds, you can and will usually put these into one integral and just call it this. That's area between, but instead of upper minus lower, it's outer minus inner, okay? Because R is all about distance from it. So area between is something like 1/2 r outer squared minus r inner squared, but those will be in terms of theta, so it's d theta. And the limits of integration are also theta. Theta 1 to theta 2. Okay, that's the big idea, and it applies to some of these. Ready? Here we go. Would you tell me what r equals 2 graphs like? Circle with what characteristics?
In the middle.
2. 2 is not a characteristic.
Radius of 2.
Radius of 2 centered at the origin. Okay. Okay. What about r equals 4 cosine theta? Radius of 2 centered at 0, 2, right? Symmetric at the x-axis. Do you concur they should be the same size, which mine, of course, do not look like? Does look like a Venn diagram.
Oh, it's an
Okay. Do you agree? Okie dokie. Now, this is going to be the same. Might as well graph all these. These are always going to be the same for all three of these first graphs. R equals 2. And so, should have handed out the compasses.
It's hard enough already.
Oh, that's 3. Dump on it. You can. Okay. Are we cool?
Yeah.
Alrighty then. Now, there are lots of different types of problems. There's inside this one, but outside that one, or outside this one, but inside that one, or inside both. So, consider the area inside R2. Now, that's inside the cosine circle, but outside the blue circle. Shade it, please. Shade it in a spokey kind of fashion. Inside the cosine, but outside the 2. Wouldn't that look more like this? We? All right. These are terrible spokes. They're not what I did there. I'm going to go. Okay. Spoken.
I think all of us heard smoky.
Did I say smoking? Oh,
I think
I just thought like.
Okay. Smoky way. No, you want. All right. So, let's go with yield setup. What do you reckon? First of all, is there some symmetry to be had here? There is. Top half, bottom half. So we'll use symmetry. We'll go 2 times a half. Okay? So we're really looking at just this upper half here. And we're going to double it. Cool? Okay? From where to where? 0, 2.
Oh, we're up to the bottom.
We need the intersection point. Okay? 2 equals 4 cosine theta at theta equal pi over 3. Yeah, so scary. Inverse cosine of 1/2. Pi over 3. Cool? Integrand, what is it?
16.
The outer is the 4 cosine theta, so 16 cosine squared minus 4. Okay?
Wait. Can we start talking?
Yes, you'll be able to use your calculator. Okay? No big deal so far. Any questions? Yes. The pi over 3, the region ended. I was getting spokes, and the region ended at that intersection point. So that came from setting the 2 equations equal. 2 equals 4 cosine theta. Yes?
Why couldn't you just say, like, all the way up to pi over 2, and then subtract, because then wouldn't you still be subtracting that like little center part where there is no spokey stuff?
Good question. So, I'm glad you asked. Could we just go pi over 2, because that would be here, here, here. So what if I did tilt pi over 2? Once I got to this region, would these red R's be smaller or greater than these blue R's? Smaller. And so when I started doing red minus blue, I would start to pick up some negative area. And so I would actually start to, if I went to pi over 2, I'd be taking small squared minus bigger squared, and I would start to reduce the real area. See what I'm saying? Okay. I'm glad you asked. Thank you. Okay. Let's go with another. How about the area inside R1, the R equal 2, the blue circle in my case, and outside R2? Shade that, please. In a spoke, it's so important that you do spokes, okay? So I start getting spokes here, and then here, and then here.
Was this slope just on the angle line? What's the point of the slope?
Yeah, well, you could draw them anywhere.
So why is it so important?
Good question.
Just color it. You can see
Coloring
it's
is
out.
Okay, so yeah, let me take you back to starting calculus town. If you had the square root function and a line, and I said this region R in x terms, how many integrals? 2 integrals, do you agree?
Yeah.
Why? Two different curves, two different situations of what curves you're dealing with. You hand off into a totally different curve, right? Okay, so here, how many integrals? 2. Gotta use 2. Okay, here, look at this little baby blue. Is it all the way to blue? Or blue, take away red? Blue, take away red. You've got to do blue, take away red up to here. But then
you double it for.
okay, doubling it would deal with this guy. But now, what about over here? Is this blue take away red? It's just the blue. Okay, so here, I go from here to there, no red.
So why can't we? Oh my gosh.
You can use geometry. You can absolutely use geometry, yes.
So that's why you don't want to let a pile pass.
Right, because you don't want to start picking up unwanted area and unwanted territory. The area we're talking about ends there, does not continue over here. Okay? All right, so let's go with this. Yep.
Could we just like shift it over to the left 2 units and take a look?
So that's what Jack Moran said. Shifting horizontally and polar.
But it's the same area as that, so we just like found the equation was negative
It's
cosine theta.
this is the same area as that.
Yes.
Yeah, why didn't we have to do it for that?
Different. I don't want to assume. So you're right in this case because the circles are the same. You could, but I don't want to do it that way. Yes.
Can you explain the whole 2 integral thing one more time?
Sure, no problem. Okay, so the whole process of where I'm getting areas starts in a turning kind of fashion because it's about theta, it's not about x's and y's. I'm not going horizontally, I'm going turning. So I'm going to start by thinking, all right, when do I start picking up this shaded area? Do you agree, first of all, with where the area is? Okay, so going in a clockwise kind of fashion or counterclockwise fashion, I start getting area. The minute I get to this section, I'm getting little sections of slivers like that. Now, to find the area for those, I would have to take the total area all the way to the blue and remove that part in the red. Because it's not, I'm not taking this area, I'm taking just this little wedge of it. Okay? Now that changes once I get to here. Once I get to here, then I'm just straight up doing the blue. I'm not taking away the red anymore. It's all the way out to the blue. Now because of that handoff into a totally different situation, that's right too.
So then when you get down to the bottom again, at that little like section, so you're just multiplying your top one by 2 to get both those sections.
You could, if you doubled it, there is symmetry, and so if you found this, you could double it to get this. Yeah. Okay? Yes.
Okay, so then I don't understand why we didn't have to use that on the first one, because aren't the little red bits cut off by the blue?
The red bits are,
Hi.
let me. It's a little convoluted here.
Yes.
Oh, shoot, I meant to color this. Sorry, give me 1 minute. All these questions will pay off dividends later as we stop making, you'll make less and less mistakes if you ask. Okay, so if I spoke, I go here, 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 here,
Yeah, and
here,
those,
here.
those right there aren't full red lines.
No, that's why I'm subtracting.
So then isn't it the same on the, I don't understand the difference of like why the integral symbol is different between them.
It's a different outer and inner. This one, the red is outer and the blue is inner. And as far as different situations, there's only one situation. The red is always outer until I found the area. So that's one integral because it's always the same outer, always the same inner. This is different because here I'm getting the outer is blue, the inner is red, so I need to do some subtraction there. But the minute I get to here now, these guys have nothing to do with the red. I feel like I'm saying it the same thing. You don't have to subtract anything over here.
So why can't you just do one integral and then just like add those areas in zero?
Add what area?
Okay, so then why couldn't you just do one integral and then add those areas where the blue radius goes all the way out and is affected by the red? Yeah, wouldn't you just say like, well, that in those spaces, like the area inside doesn't need to be. Oh, wait. It would just be zero. That's what I'm saying.
Oh, yeah, you couldn't subtract the whole, you're saying subtract the whole.
Like, why can't you just do an integral from like up there all the way to, why can't you just do one integral? Because then once you get over there, you pass the center line where you like start to have like the full spokes.
Yeah.
Then you would just be subtracting nothing.
So, but you wouldn't be subtracting nothing. There's something here. This red is something. It's negative. See, it's not like the red. I think you're thinking that once you get here, the red just doesn't exist anymore. And in fact, at these points, the red is here. These are at these angles. You're backing up into the circle. So if you did blue minus red the whole time, then here you'd be good. But now you're talking about blue, take away the square of that. And so that's, I mean, obviously that's not what you want to do. You know what I mean?
How do you decide what direction the spokes go?
Always from the origin. What do you mean? What direction is supposed to go? That would come out from the
Wait,
origin.
so I'm just still confused. Why do we have why can't we just save it?
Spokes tell you when you're starting to get one integral and starting to get a different. Okay? All right. So from 0 to not 0, where's the start? Let's focus. Let's go. 5 or 3, 2. 5 or 2.
Oh, no.
Outer minus inner.
4 minus.
4. Oh yes, I agree. This starts.
Okay.
We're 8 or 6. We're
2.
16 cosine squared of theta.
2 plus, what's that? 4 cosine theta, my bad, sorry. I was thinking my next example. Squared d theta, that covers this little wedge, and if I double it, if I double it, that covers this and that little wedge. Do you agree so far? Okay, now I need to add a half circle, which you can certainly do geometrically. 1/2 pi r squared, where in that case the r is 2. Okay, so far so good. Okay, yes?
So could you do just pi squared minus, like, if you look at the same thing in the Venn diagram in the middle, could you separate that into fourths and then find one based on one function, multiply that by four, subtract that from pi squared? Does it like work that way? Is there like
Say that again, let me think about it.
so like the inside can be divided into fourths, right? Will we get the same? The whole circle can be divided into fourths, like one at the x-axis and then one straight there.
Here and here, or here and here?
Like one at x equals 1,
Okay.
and then one at so y equals 0.
Y equals 0?
Yeah, so you separate that into 4 parts, and you do pi squared minus 4 times the integral of 0 to pi over 2 of 2.
I have to think about that. I'm not sure I see it, but I'm losing people, so let me think. Okay, here we go. Let's try another one, please. Okay, besides area between, you also have to do area and. This is a crucial word. It's and, it's not or. If you want the area inside both, then any point you find has to be inside both. Okay, so for example, this region here, do you agree that's inside one and the other? But this point is not inside both. It's supposed to be inside both. Understood? And both. Okay, so in terms of spokes, I get to the blue, 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 until then, where I start to get to the red. Okay? That's why you draw spokes. Okay?
Yeah. We have there's another way, Smash, I think. Could you just do the quarter circle and then subtract the first integral from the second one? From the second
A
problem?
quarter circle.
Because you're removing that little chunk
Okay.
like from the quarter circle.
This
So you're removing that.
and
from the
moving
quarter.
that. Yes, you could.
Wait, can you say
Yeah,
that?
So could you find this quarter circles area, 1/4 pi r squared, and remove this little wedge we found over here?
Mr.
This, that's what we found.
It's the same equations as part B, you just reverse them and subtract the wedges from the power.
Because, it's not a fourth because we start with, I see what you're saying. Yes. Now, I agree, and so let me say this. If you have, it's often the case that if you have one piece, you can use it for a second piece. But the way I'm going to set this up is kind of like they're going to come in the AP test, which is it's just its own little problem where you don't have anything to build off of, okay? So you're absolutely right. But let's pretend like we had nothing to go off of, okay? You would typically then find an area like this by going outer until you get to a different region and picking up a second region. Are you with me? So this first blue region, how would you find the area? 2 times a half because there is symmetry. From where to where? Starting, the blue starts at 0 and goes to pi over 3, and it's inside the blue, which is 2. Are you with me so far in the blue? Okay. Now I need to add the green. 2 times a half. There is symmetry. From pi over 3 to pi over 2. You're going green until you get into the origin, which is at pi over 2. And that's inside the red circle, so 4 cosine theta.
Wait, can you explain the pi over 2 for me?
Sure. So you're starting to get green the minute you're facing pi over 3, right? And because, remember this is the equation. As cosine gets smaller and smaller, those greens are going to get smaller and smaller and smaller and smaller until you get to pi over 2 where cosine zeroes out. That's what you do. Okay. That's a no calculator example of different questions that would usually come separated, not building off one of each other. Are you ready? Are you with me?
Wait, did you say no? Did you say no count?
They would just be set up variables. You wouldn't have to do it. Okay? The intersection point to be found by no calculation. Okay?
So that's 16%.
Okay. For these, would you got your calculator, please? 2 plus sine and 4 cosine.
That's what he got on the board.
Oh, wait, divided by 2. Equals,
Go to polar
so it's 8.
mode. 2 plus, help yourself, please. Are you good? It might be already done for you, but start again. Okay. Oops. The theta, I remind you, is in the pi. One place to find it is in the pi submenu. Okay, so convex Limassol and a 4 cosine in the pi button.
No, because you only find 1 quarter.
So if you're doing 1/4, then you don't use this, you just do top minus bottom. But if you're doing the squaring, it's what you do for polar.
Okay, you get something like those. Okay.
Oh, wait, yeah, no, why not do this transpolar?
All right. Now, these you will need intersection points for, and we'll need to store them. So, consider going to Menu, Analyze Graph, Intersections, and find those intersection points. Yeah, it just says graph, which basically says, no, I can't do that. Okay, so the calculator will not find intersection points of polar, unfortunately. So what do we do? No, we think.
Can't you just like leave it half?
Send them equal to each other, okay, analytically. Could we still use graphing? I want to find lots of. There you go. Okay, so you can go back to rectangular, graph them in rectangular, and find their intersection points in rectangular. So 2 plus sine x. Oops. I don't know if it does that. What's really cool is it puts them on top of that. That's even better. 4 cosine.
Wait, you just do the same,
Put it in function mode.
like you do the same.
With the same equations, okay? Because where they'll be equal in function mode, it'll still be the same numbers as in polar mode. Obviously, it means totally different graph, but the numbers will be the same. Now, the question will be, obviously we have multiple intersection points. Which one should we find in order to correspond to these polar intersection points? So this one. Do you want to go all the way around positive version, which I suppose would correspond with that intersection point? Or do you want to go the negative intersection point, which would be that? The negative one? Okay. So would you find that intersection point then to find this polar point we're looking for? It's a choice, but as far as this intersection point, if you did it in a positive way, you start at 0 and you'd have to go all the way around, so that would be more of a close to 2 pi intersection, a big positive one. But it's quicker to just start here and go negatively boom right there. Now a small negative then would mean I want this intersection. Okay?
Okay, Mr.
Yes.
What's wrong with studying them equal to each other? Or like subtracting one and then finding the.
So if you did like just analytically, is that what you're saying?
No.
Set the equations equal to each other? What are you saying?
Well, like subtract one from the other and instead of using 0 and
And find the 0? Yeah, that's fine too.
Oh, I said that. You said no.
Oh, maybe I didn't understand. I thought you were doing this analytically, inverse tangent of blah, blah, blah. Okay. All right, so store those please to whatever A and B. There's the first one is roughly 1.4-ish. Did you agree? Do I have that right? Negative 1.4? Oh, that sounds more familiar. What did I do wrong? Oh. Oh, I sure did. That's why I moved the graph. Oh, I didn't mean to move the graph. My bad. You did? I'm so used to ignoring you, I didn't. Sorry. A. So negative 1.3 on that is A. That's what you get for being bad. All right. Then the intersection point.
What do you say, Corey?
Mr. Rickman, buddy. We are going to step outside. Boom and boom. Did you get 0.819 for the other?
Pick the two intersections that are closest to it.
Closest to the origin, I believe, is probably the best way to go.
Okay.
Okay? Oh, shoot. I did that badly. Okay. Do you have those stored to A and B?
Yeah.
Okay. All right. Let's pick up with our...
Wait, can you explain what I know which one is which?
Which one's which? What? What do you mean? It is pretty convoluted, I gotta say.
How do you pick your intersection point?
Okay, in terms of, so we're looking for these two polar intersection points, right?
Yeah.
Okay. For this point, that's pretty obvious. It's the first positive intersection point. 'Cause remember, theta starts at 0 here. It goes that way. So that intersection would be the first positive intersection. So that's why that's that. Okay? For this one, I could look at it two ways. I could start at 0 and go negatively to find that intersection point. In which case, that would correspond to that one. Because it's a negative intersection. So that's that. I could have gone 0 to all the way around, and that would be the second positive intersection point. That would have been that one. But we just said closer to the origin is better. Does that make sense? Negative angle, negative intersection point. There's the negative intersection point. That's the negative angle. Okay? Okay, here we go. Real quick sketch. 2, 3, 2, 1. 2, 3, 2, 1. Oops, 2. 2, 3, 2, 1. Red, 4 cosine theta. 4 cosine theta. 4 cosine theta. Okay, cool. Alrighty then. Here we go. Are you ready? All right.
I'm still drawing.
We're not gonna be graded on the,
Accuracy of your graphs. You should be.
but I mean,
Oh,
you
shoot.
draw it.
We're so out of time. All right, or running low on time. Okay, so here we go. Imagine we know this angle and this angle. This is, I had it stored as. Did I find that one first? Is that A?
Okay.
This is A. That's A for me, and this is B. All right. Okie dokie. If I said area inside the R2, which is the inside the red circle, but outside the limacon. Inside the circle, outside the limacon. That would be in this region, yeah? Okay, draw some slopes. Boom, 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 boom. Symmetry to be had?
Yeah.
No symmetry. There's no symmetry. Okay?
Oh, yeah.
Okay. There's no symmetry in that region. You're going to have to do the whole region. Okay? Second, one region or two. Is it always the same outer and inner? Or is there a handoff? It's always red minus blue. Okay, so we can go from A to B. There's no doubling. It's just 1/2. Outer minus inner. The outer is 4 cosine of theta squared. The inner is 2 plus sine theta. squared, boom, straightforward. Very cool? Okay, now, as we go to these, we have a result that might help us do these, but let's just pretend like we are just starting from scratch each time, okay, again, because that's usually the way they'll come. Say I said area inside R1 and outside R2 then. That's inside the limacon, outside the circle. So if I were to spoke that, it would be whoosh, 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 whoosh. Ay, ay, ay. I'm a little worried about that. There's a little bit of honor minus center there. I'm not showing the
The
picture.
center is always the same value.
Okay? So how many regions? Three. Okay. There are three. So let's talk
Big idea.
region 1. Region 1 goes from where to where?
From B to 5.
B to pi over 2. And it's R1 minus R2. Each one squared. Okay?
Yep. Are all the areas like wherever, like the areas in between the area in between the circles? Isn't that the same as if they were shifted to like the first 3 problems that we did?
But the limacon is not a circle.
Okay, that's
This is a circle, but this is convex. It's more of an H. Yeah, it's not a circle at all. So what about the region 2? Pi over 2 to 3 pi over 2. I agree. What's the integrand? Just R1, right? No inner. Okay? And here's the last part. Don't be fooled. Limits.
Negative pi over 2 to A.
Perfect. Okay. You can't go 3 pi over 2 to A because that means going from a greater number to a lesser number. That's d theta is negative. You're going to get negative area that way. Okay. So that's a no-no. You can either go 3 pi over 2 to A plus 2 pi, okay, or most people prefer to go negative pi over 2, or negative pi over 2 to A, and outer minus inner. All right, that should be good to do your homework. We'll do extra practice tomorrow.
R1, right?
In this case, down here,
Yeah.
outer is, I forgot what I was doing.
R1's R1 is R2.
Yes,
Okay.
yes. It's the blue minus the red. In this little region, I didn't show it very well, but it's the blue is outer, the red is inner.
We didn't even finish the front.
Yeah, that's rough.
Where's the back though?
Nope, that's true. We'll finish. You should be able to do your homework. Have a nice day. Yes, sir.
So the thing I was thinking about was because there's 2 axes, so much one axis is 1, it's going to be like 4 component parts, and then you multiply the total difference. You find the area, I find it which is 1 to 2. Which I think is the same answer.
That for circles, it's such nice.
Yeah, but not for one.
Yeah, we just done the equation for any single circle. So I agree, that was pretty well. Real pretty easy. That was pretty just go. Hi.
For this one, so you couldn't go from 3 pi over 2 to A because A was a smaller number. So, but what if we would have chosen like the later,
Then you
we
could
would
have,
have.
yes, you could actually find A to and C. Somebody in the last class did that. That would have been pretty smart because then you could have gone. Then what would you have? Had that last one in C. It would just confuse you. Then you could have gone 3 pi over 2 to C.
Right, I don't
wanna do that.
Wait, so why would you do A, B, and?
Well, so if you wanted to refer to this both, sometimes it's a -1 and sometimes it's a positive. Like here, for example, it was nice to let A be just a little negative. But here, in this case, we kind of want that one to be a big positive. So it would make sense then to store that intersection once is the negative little one at A, and then later is the bigger one at C. So that here you can use A, but here you can use
Okay.
C.
That makes sense.
Okay.
Cool. Thank you.
You're welcome.
Mr. Rickman?
Yes, sir.
So, I was wondering if you had time to fill out this recommendation.
Sure.
Thank you so much.
No problem.
Executive.
What's the date on it?
Oh, okay, so the recommendation is to,
I have one.
it's supposed to be somewhere on here.
Let me- She says the 20th. Somebody told me it was the 20th. Is that true?
That makes sense.
Okay. I can do that, no problem.
Apparently they're really long.
Mr. Rickman,
Yes?
I'm like, I have to go tutor in that right now.